Good morning, sir. The topic for my case study is deep learning based robust positioning for all weather autonomous driving vehicles. This is my base paper, deep learning based robust positioning for all weather autonomous driving. Um, First of all, let me explain what is positioning. Positioning is a method to knowing the exact position of the self-driving cars through GPS and all. In some weather conditions, the GPS are not working properly, but for that we imply deep learning based method for this limitation. Overview of this paper. This paper addresses the crucial challenges for the autonomous vehicles, that is not knowing robust positioning in all weather conditions such as rain, fog, and weather conditions. The autonomous vehicles are heavily on precise localization, and this is typically achieved through ego motion estimation using onboard sensors like cameras, lidars, and radar. However, weather conditions often degrade the performance of these sensors, particularly camera and lidar, which struggles in poor visibility. In fact, in such cases, in snow and all, the camera is not visible under the snow. That's why it struggles in poor visibility. The proposed solution is a geometry-aware multimodal ego motion estimation GAM. There is a framework that fuses the complementary strengths of visual sensors and lidars. Using an attention-based learning method. The framework employs self-supervised learning, meaning it does not require ground truth label for training, making it scalable and practical for large data set. It shows improved robustness across 5 environmental conditions: that is the day, night, rain, fog, and snow. The objective of this paper is all-weather robustness, achieving robust ego motion estimation in various environmental conditions, multimodal sensor fusion, combining data from multiple sensors to create a more reliable localization system, self-supervised learning, eliminating the need for manually labeled ground truth data, making the system scalable. And the methodology for this paper, multimodal sensor fusion method fuses data from camera, lidar, and radar using an attention-based deep learning model to leverage the strength of each sensor, where radar is robust to adverse weather and the camera provide rich visual data. Self-supervised learning. The approach employs a self-supervised deep learning framework using geometry-aware view reconstruction to predict ego motion and depth without the need for manually labeled ground truth, making the system scalable. Multimodal and modular design. The system uses a modular design where each sensor predicts ego motion independently, allow for robust performance even when some sensor data is missing or unavailable. Limitations of this paper is sensor reliability. Although radar is robust in poor weather conditions, it is still limited by its lower resolution compared to the camera and lidar. This may affect fine-grained positioning accuracy, particularly for objects at longer ranges. In longer ranges of objects, this sensor won't work for the longer ranges objects. Data dependency. The system's performance is highly dependent on the quality and quantity of data, especially for rare and or extreme weather conditions like heavy snow or fog. While the model is self-supervised, the availability of diverse data is crucial for because this model is trained based on some limited number of data. So that's why this is the limitation for this paper. Complexity and latency. The multimodal approaches increases the computational complexity, especially when handling data from multiple sensors simultaneously. This can introduce latency in real-time system, which may be a concern for AVs. Limited to self-specific sensor configurations. The model assumes the use of certain sensors with a specific configuration. It may not be easily adaptable to other sensor type without significant retraining, because some sensors are not adaptable for some situations. So we can retrain the model for getting the correct output. Generalization to extreme weather. While the model performs well in simulated fog, rain, and snow conditions, it may still struggle with the more extreme or less common weather phenomena. This model is employed in the simulation environment. It is not employed in real-time environment. Okay, move to the paper one. The paper one title, and this is my paper one. The title for the of the paper is a deep camera radar fusion with attention framework for robust object detection in adverse condition. The overview of this paper introduces a deep learning based fusion framework that combines camera and radar data for robust object detection in challenging weather conditions such as fog and snow and rain. The fusion of these sensors is achieved using an attention mechanism that allows the system to weigh the importance of each sensor based on environmental conditions. Objective of this paper is improve object detection accuracy, enhance the ability of autonomous vehicles to detect and classify objects accurately in adverse weather conditions by combining camera and radar data. Leverage sensor strengths, utilize the strength of camera and radars to complement each other, providing more reliable environmental perception under low visibility scenarios. Develop an attention-based fusion framework, that is, create an attention mechanism that adapts to changing weather conditions, allowing the fusion system to weigh and prioritize the most relevant sensor data for accurate object detection in real time. That is, make the sensors for suitable for all weather conditions. And the methodology proposed here is a multi-modal sensor fusion. That is, the paper integrates data from cameras and radars using deep learning techniques. The camera provides rich visual information while the radar offers weather robustness, ensuring reliable object detection in adverse conditions. Attention based mechanism, the model uses an attention framework that dynamically assigns different importance weights to the camera and radar data based on environmental conditions. This ensures that the model prioritizes the more reliable sensor data in each scenario. End-to-end learning, that is, the fusion model is trained to end-to-end, meaning that the system learns to detect objects directly from raw sensor data through the attention based fusion network. The limitations of this paper is the radar resolution. So that is, despite radar's robustness in weather conditions, radar has lower resolution compared to cameras, which may lead to challenges in detecting the small objects or fine details in the environment. Sensor calibration, that the performance of the fusion system is highly dependent on accurate sensor calibration. Inaccurate calibration between camera and radar can lead to mismatched data, reducing the model's effectiveness. So that is, the calibration is not done perfectly. So the limitations are, so the challenges we are so this is a challenge we are facing in sensor calibration for this proposed model. Environmental dependency, the effectiveness of the attention mechanism relies on accurate detection of environmental conditions, that is, extreme or rare weather conditions that were not part of the training data might affect the system's ability to adapt. And this is my paper 2. The title of the paper 2 is Comparative Analysis of Deep Learning Based Vehicle Detection Approaches. The overview of this paper is, this paper provides a comparative analysis of various deep learning models for weather classification in the context of autonomous driving. It evaluates different architectures, that is, CNN, RN, and hybrid model for their ability to classify weather conditions such as rain, fog, snow. The goal is to improve the ability of autonomous vehicles to adapt to the diverse weather conditions, which significantly affect sensor performance and decision making. Here what it explains is, this is a comparison for all type of different kinds of architecture to overcome this issue. The objectives of this paper: compare deep learning models, that is, to compare the effectiveness of CNN, RN, and hybrid structures for classifying weather conditions that impact autonomous driving. Improve weather adaptability, to develop models that enable autonomous vehicles to better understand and respond to various weather scenarios, thereby enhancing safety and reliability. Enhances model robustness, that is, to assess how well these deep learning models can generalize across different weather types, and improve the AV systems adaptability to make real-time driving decisions under adverse conditions. The methodology employed here is model comparison. That is, the study compares different deep learning architectures, like including CNN, RNN, and hybrid models, in terms of the ability to classify weather conditions. Each model is trained on a large data set that include it's labeled weather conditions. Data augmentation to simulate various weather conditions. Data augmentation techniques are used to generate new data points, ensuring the model can generalize well across different weather types and sensor configurations. Performance evaluation. Each model's performance is evaluated based on its classification accuracy for different weather conditions. The models are tested on a validation data set to measure how well they adapt to unseen weather conditions. Limitations. Limited weather scenarios. The study might not cover all possible weather scenarios that autonomous vehicles might encounter. For example, extreme weather conditions like hail or very dense fog could be represented in dataset. What it explain is some architecture won't clearly learn the what the weather condition is. That's why they are not. That's why they might encounter this limitation. Generalization to real world data. While the models perform well on synthetic or augmented data, so they may not generalize as effectively to the real world data, especially when the weather conditions are more complex or different from those in training set. That is, they are the data set is different from the original from original weather conditions. So the model is not well trained on the adverse conditions. So this is the limitation for this. Imbalanced data. The data set might have an imbalance in the number of samples per weather type, leading to biased model performance, favoring weather types with more data. That's why what here what it explains means the data set might have fewer number of fewer number of weather types. So that's why the limitations are. This is the paper 3. The paper 3 titles is a deep learning based approach for autonomous vehicle localization, application and experimental analysis. The overview of this paper is presents a deep learning based approach for autonomous vehicle localization, focusing on enhancing positioning accuracy in various environmental conditions. The proposed method utilizes a long short-term memory networks to process the sequences sensor data, enabling the AV to estimate its position more effectively compared to the traditional methods. The approach is evaluated against ground truth, demonstrating its potential and improving localization robustness and in dynamic driving scenarios. First of all, what the LSTM means. The LSTM means a long short-term memory is a special type of RNN used in deep learning for processing and predicting sequential data. Why this is employed here means standard RNN struggles in a long-term dependency because of the issues like the vanishing gradient problem. LSTM solved this by using a memory cell that can maintain information over a longer period of time. Objective of this paper is enhance localization accuracy to improve the positioning accuracy of autonomous vehicles by leveraging deep learning techniques. Utilize sequential sensor data, that is to process and integrate sequential data from various sensors using LSTM network for better localization performance. Evaluate performance to assess the proposed method's effectiveness by comparing its localization estimates with ground truth data. The methodology employed here is data collection. Gather sequential sensor data including information from GNSS, IMU and odometry system. Model development. Develop a LSTM based deep learning model to process the sequential and predict the vehicle's position. Training and the evaluation. Train the model on the collected data and evaluates its performance by comparing the data predicted position with the ground truth measurement. Limitations. The limitations are sensor dependency, that is the method's performance heavily rely on the availability and accuracy of sensor data, which may affect by environmental factors. So sometimes the sensor have one such environmental factor, but in real time it is different. That's why So the sensor dependency is a limitation here. Computational complexity. Training a deep learning model can be computationally intensive, require significant resources. Generalization. The model's ability to generalize across different driving conditions and environments need further validation. Paper 4. The paper titles of my paper 4 is Deep Learning for Autonomous Driving System. This paper discusses how deep learning techniques are revolutionizing autonomous driving system. It reviews the various deep learning models used to process sensor data for tasks such as perception, localization, motion planning, and decision making. The paper also emphasizes the importance of large-scale dataset and the challenges of real-time processing is in autonomous driving, especially in complex urban environment and adverse weather conditions. Objective of this paper: a review of deep learning models, that is to review and categorize various deep learning models that are applied to autonomous driving for tasks like perception and decision making, improve perception and localization to improve the vehicle's ability to perceive its surrounding and localize itself accurately in real time using a sensor data and deep learning techniques. Enhance decision making to show how deep learning models can be used for motion planning and decision making to improve vehicle control, safety and efficiency. Methodology of this paper: data processing utilizes deep learning models such as CNNs and RNNs to process data from various sensors including camera, lidar and radar. Task specific model implements separate deep learning models for specific tasks, object detection and segmentation for road signs, pedestrian vehicles, localization accurately determined by the vehicle's position, motion planning and control, predicting the best route and control the vehicles. Real-time processing discuss the importance of optimization deep learning models for real-time inference on embedded system, which can be a major challenge for large-scale dataset in autonomous driving. Limitations of this paper is data dependency. Deep learning model require large amount of labeled data, which may be difficult and expensive to obtain for autonomous driving in a diverse environment. Computational complexity: the real-time processing of sensor data from multiple sensors, especially in complex environment, requires significant computational resources, which can be a bottleneck in embedded system. Generalization issue: while deep learning models perform well in the training environment, generating to new unseen environments remain a significant challenge. This is paper 5. The title of the paper 5 is Multimodal End-to-End Learning for Autonomous Steering in Adverse Road and Weather Conditions. This paper presents a end-to-end deep learning approach for autonomous steering in vehicles under adverse road and weather conditions such as rain, fog and snow. The proposed model integrates visual and lidar data to enable the vehicles to make real-time steering decisions while adapting to varying driving conditions. The research emphasizes multimodal learning, allowing the model to leverage data from multiple sensors for better decision making even in challenging environment scenarios. The objective of this paper: end-to-end autonomous steering, to develop an end-to-end deep learning model for autonomous steering that works seamlessly in adverse weather and road conditions, ensuring safe driving decisions. Multimodal sensor fusion, to combine camera and lidar data for improving vehicle perception, enabling more reliable autonomous navigation under difficult conditions such as poor visibility, adverse condition adaptability, that is to enhance the model's ability to adapt to environmental challenges like fog, snow and rain, improving driving safety and efficiency. Methodology is multimodal data fusion. That is, the model uses visual data from cameras and depth data from lidar to create a robust understanding of the road environment. By fusing these two sensors modalities, the model enhances its ability to detect objects, obstacles and lane boundaries in varying conditions. End-to-end deep learning, and that is, the system is trained end-to-end, meaning the input data is processed directly through a deep learning network to output steering commands. This simplifies the pipeline and ensures fast decision making. Adversarial weather simulation, to ensure robustness in all weather conditions. The training data set is augmented with the simulated weather effects such as rain, fog and snow. The model learns the learns to handle these conditions during training by being exposed to weather related challenges in data, limitations in sensor dependency. The system's performance heavily depends on sensor quality and calibration. Inaccurate sensor readings, and especially under extreme conditions, could lead to poor performance. Real-time processing. End-to-end model requires significant computation power, which may pose challenges for a real-time deployment in autonomous vehicles, especially on the resource-limited embedded systems. Data augmentation limitations. That is, while simulated data is used to augment the data set, it may not perfectly capture the complexity of a real-world weather condition, leading to a possible performance gap when the model is deployed in the field. This is my paper 6. The title of my paper 6 is Probabilistic End-to-End Vehicle Navigation in Complex Dynamic Environment with Multimodal Sensor Fusion. This is related to the previous paper. This paper proposes a probabilistic end-to-end navigation model for autonomous vehicle that operates in complex dynamic environments using multimodal sensor fusion. The proposed model integrates camera, lidar and radar data to improve the vehicle's ability to navigate through challenging environments. By treating the navigation problem probabilistically, the model can account for uncertainties in the sensor data and the vehicle's movement, which is essential in dynamic environments where obstacles and conditions change rapidly. The framework is designed for real-time, robust decision making and motion planning in urban setting and dynamic traffic. The objective of this paper, probabilistic navigation, to develop probabilistic end-to-end model for vehicle navigation that can account for uncertainties in sensor data and vehicle movement, allowing for safer and more reliable decision making. Multimodal sensor fusion to integrate camera, lidar and radar data into a unified navigation system that improves perception, obstacle avoidance and decision making. Real-time performance, to design the system for real-time operation, ensuring that autonomous vehicles can navigate dynamically changing environment without delay in decision making. And the methodology is multimodal sensor fusion. The system uses a fusion of sensor data from cameras, lidar and radar to improve the vehicle's perception of its environment. The method is the data is processed and fused to create a comprehensive understanding of obstacles, road conditions and traffic. Probabilistic model. The model is built to handle uncertainty in sensor data and environmental conditions, employing probabilistic method to estimate the vehicle state and plan the best trajectory. End-to-end learning. The model is trained in an end-to-end manner, meaning that it directly takes the input from sensors and output navigations and decisions such as steering, acceleration and brake commands. Limitations of this paper: data quality and availability. The performance of the data is highly dependent on the availability of high quality sensor data, and in environments with a sparse of or noisy data such as heavy rain or poor lighting, the system may not perform optimally. In adverse conditions, that is a noisy data, it is when it is a some blurred images in the data set, then we might face this issue. Real-time processing, although designed for real-time operation, the multimodal fusion and the probabilistic modeling can be computationally expensive, potentially limiting performance on hardware with lower computation resources. Embedded systems. Generalization or to all environments. The system may struggle to generalize to unseen environments or highly dynamic situations that were not covered in the training data, such as unusual traffic patterns or extreme weather. This is paper 7. The paper 7 titles is an efficient domain incremental learning approach to drive in all weather conditions. This paper introduces and domain incremental learning (DIL) approaches that helps autonomous vehicles improve their ability to drive in all weather conditions. The paper explores how the AV's system can adapt to different weather scenarios by incrementally learning from new data without forgetting previous learning. That is, it takes real-time data from adverse conditions. That is, it can store the previous data and collecting the new data without deleting or forgetting this previous data. The approach uses an incremental learning technique to train AV model on diverse weather dataset, ensuring better generalization to unseen weather conditions and environment. The model is built to work in an adaptive manner to maintain high performance despite the changing nature of weather and road conditions. Objective of this paper: domain incremental learning, to propose a domain incremental learning framework that allows autonomous vehicles to adapt to new weather conditions continuously without forgetting the learned knowledge from the previous data, like it is like LSTM, improving generalization to weather conditions to improve the ability of autonomous driving system to generalize to unseen weather scenarios, ensuring safe operation across diverse conditions. Efficiency in learning, to develop a method that can effectively handle the challenges of incremental learning, ensuring that the AV's system adapts to new conditions efficiently without requiring extensive retraining. Methodology proposed here is domain incremental learning. The core approach is based on domain incremental learning, which adapts the AV model incrementally as new data and without forgetting the old data or collected data. This allows the model to improve over time, adapting to the new data that is captured or collected from the collected in the real time. Incremental model update: the model is trained in a small incremental steps, allowing it to process data efficiency without needing to retrain from scratch each time new weather data is introduced. This method helps prevent catastrophic forgetting, where the model forgets previously learned knowledge when trained on the new data. Cross weather generalization: to ensure that AV system can generalize to new unseen weather conditions, the system is exposed to a wide variety of weather related data during training, enabling it to make accurate predictions and decisions regardless of the environmental conditions. The limitations of this paper: data imbalance. There may be a significant imbalance in the amount of data that is the collected data or the data sets we are having is not balancedly it's not balanced. That's why we facing this issue. The model is not the that's why the in case of imbalanced data, so the model is not trained well. That's why we facing this issues. Computation complexity: while domain incremental learning aims to be efficient, incremental updates and managing large data set from multiple weather conditions can be computationally expensive, particularly when applied to real-time systems in autonomous vehicles. Adaptation to extreme weather: the model may still face challenges in extreme weather scenarios or rare events where sensor data may be inefficient, leading to potential performance degradation. That is, the model is not trained in all type of weather conditions. That's why we're facing this issue. And this is a paper 8. The title of the paper 8 is Deep Learning Sensor Fusion for Autonomous Vehicle Perception and Localization. The overview of this project is this paper provides a comprehensive review of the deep learning based sensor fusion techniques used in autonomous vehicles for perception and localization. The review focuses on how combining data from different sensors can enhance the AV's ability to perceive its environment and accurately estimate its position on the map. The paper discusses various improving AV localization in diverse driving environments, especially under adverse weather conditions. Objective of this paper: review of sensor fusion techniques, to review state of the art deep learning based sensor fusion techniques used in autonomous vehicle systems for the improving perception and localization, evaluate fusion strategies, to evaluate different fusion strategies and assesses their advantages and limitations in the context of autonomous driving, improve localization, to examine how sensor fusion can improve localization in accuracy in complex environment, particularly in urban scenarios or adverse weather conditions. Methodology is the sensor fusion model. The paper categorizes different type of sensor fusion model. Early fusion that is combine sensors at the feature level before feeding it into the deep learning model. Late fusion fuses the output of the individual sensor models after they have made independent predictions. Joint fusion means integrate both the data and the output layers during the learning process for more accurate predictions. That is, early fusion means the integrate the combine sensors data at a feature level, that is in starting level we can feeding it into the deep learning model. And late fusion means the output of the sensor is feeding in the say deep learning model. Joint fusion means we can combine these both we can combine these both models, that is these two fusions, that is early fusion and late fusion, to process for more accurate prediction. Deep learning architecture, that is the review discusses various deep learning architectures such as CNN, RNN, and LSTM, and autoencoders used in sensor fusion tasks. These architectures help process multimodal sensor data and enable the AV to make robust predictions for perception and localization training. Evaluation of sensor fusion performance. The paper evaluates the performance of sensor fusion models in real world scenarios, including both static and dynamic environment. It highlights the strength and weakness of fusion approaches in achieving real time localization and perception. Limitations of this paper is data quality and availability. The performance of deep learning based sensor fusion models is highly dependent on quality and quantity of training data. Limited or biased dataset can affect model generalization ability. Sensor calibration is crucial for accurate sensor fusion. Inaccuracies in calibration can lead to poor model performance. The paper highlights the complexity of achieving proper calibration in a real world application. Computational complexity. The deep learning models used for sensor fusion can be computationally expensive, requiring significant processing power, which can be bottleneck in real-time application in autonomous vehicles. Generalization across environment. While sensor fusion improves the robustness of AVs in many conditions, generalization to all environment, especially in rare or extreme conditions, remain a challenge. The paper notes that the models trained on limited environmental conditions may not perform well in the engineering. That is, this model is trained on the not this model is not trained in the this model is not trained in the big data. This is trained on the small data. That's why it cannot give the accurate output. And this is a comparative analysis. For my base paper, we use GPUs and TensorFlow for the software and hardware component. The data set we used is Kitty and YMO. The key innovation is robust positioning under adverse weather conditions. Performance high accuracy in adverse weather conditions. The limitations limited to specific weather type. That is, it is for only specific weather types only. Deep camera radar fusion with for my paper 1, we used PyTorch for software, FPGA for hardware task, attention framework for camera radar fusion in adverse weather conditions. That is the data set we use WeatherNet and Kitty. Comparative analysis of deep learning models for weather classification and autonomous systems. The sensors used is camera and the software and hardware components, Keras and GPU. And a comparison of deep learning models for weather classification. The data set we used is UZ, Berkeley and WeatherNet. Deep learning based approach for autonomous vehicle localization. For my paper 3, the sensors used is LiDAR and camera, and the software and hardware components are MATLAB and GPU. And the key innovation is autonomous vehicle localization using deep learning models. And the data set we use is YMO and Kitty here also. For my paper 4, the sensors used is camera and LiDAR, software and hardware, TensorFlow and GPUs. Key innovation, deep learning application in autonomous driving system. The data set here used is, that is also a Kitty and YMO. And for my paper 4, the camera, radar and the software and hardware was PyTorch and NVIDIA end-to-end learning for autonomous steering. The data set we used is Autonomous, Oxford Robotics. And for my paper for probability end-to-end vehicle navigation in complex dynamic environment with multimodal sensor fusion. and the sensor used is LiDAR and LiDAR. The software and hardware components used is MATLAB and GPUs, like universal processing model for a vehicle navigation with sensor fusion. And the data set used is Waymo and cityscapes, an efficient domain incremental learning approach to thrive in all weather conditions. The sensors are here also. The radar and the cameras is used. Hard software and hardware is TensorFlow Cloud and key innovation domain incremental learning approach for all weather. The data set used the WeatherNet and Kitty. This is my last paper. The sensors used is cameras, LiDAR and LiDAR. Software and hardware component TensorFlow and the GPUs. Key innovation review of sensor fusion techniques for vehicle perception and localization. Data set is Kitty and cityscapes. Why I choose this base paper is comprehensive all-weather handling. That unlike the other papers that might focus on specific conditions or rely on certain sensor setups, this paper directly addresses robust positioning across all weather conditions in autonomous driving. Handling adverse weather is a critical challenge than this paper focuses on that area might make it more applicable to the real world, all encompassing driving conditions. It has a practical application in ensuring that the vehicles can still operate safely even in the worst environmental conditions. Holistic positioning, that is positioning and localization, are among the core challenges for autonomous driving system. This paper focuses specifically on deep learning based positioning, which might provide a better long term solution compared to the other papers. Proven and well used datasets. The dataset here is used is Kitty and Waymo datasets, which are industry standard datasets widely used for autonomous driving research. This means the method in the paper have been tested on large, well validated data, which enhances the credibility of the result. The other papers may use different datasets that might not be as comprehensive or might focus on more niche subset of conditions. And robustness to sensor noise. Adverse weather conditions can drastically affect the quality of the sensor data. This paper focus on robust positioning likely includes techniques to handle noisy or missing sensor data, which is crucial for practical deployment. Other papers may not address this level of robustness and may focus on ideal conditions which aren't as applicable for real world scenarios. Deep learning application. The deep learning has proven to be very effective in solving complex problems in real-time environments. Since this paper uses deep learning for positioning, it can provide insights into techniques that are adaptable, scalable, and able to improve over time with more data. This is an advantage compared to more traditional techniques or simpler machine learning approaches used in some of the other papers. This is a conclusion of this uniqueness in adverse weather handling, higher level of practical applications. So these are the solutions that have to be worked on the limitations, and enhance weather and environmental coverages, expand the data set by integrating diverse weather conditions and environments using synthetic data generation and crowdsourced data. This ensures better generalization and robustness for real world scenarios. Optimize for real-time processing. Apply model optimization techniques such as quantization, pruning, and parallel processing to improve computation efficiency, reduce inference time, and enable real-time decision making and edge device. Sensor fusion and adaptability. Integrate multiple sensors like LiDARs and cameras and radar for better robustness in adverse weather, and implement dynamic calibration and multi-sensor fusion to handle sensor limitation effectively. This is expected benefits: enhance weather and environment coverage, improve robustness, better generalization, and for the second solution, faster decision making, efficient resource usage. For the third sensor fusion and adaptability, improve accuracy. Multi-sensor ensures that the system can leverage the strength of each sensor, resulting in more accurate and reliable positioning, increased reliability in adverse conditions. And the conclusion, now we are going to conclude this. In conclusion, expanding the data set scope is a critical step in enhancing the robustness and the generalization of autonomous driving system by integrating more diverse data set and applying data augmentation techniques. Now the conclude we conclude this with in conclusion, expand the data set scope is a critical step in enhancing the robustness and generalization of autonomous driving system. Uh, in enhance, in conclusion, expanding the data set scope is a critical step in enhancing the robustness and generalization of autonomous driving system. By integrating more diversity and applying data augmentation techniques, we can expose the model to wider variety of weather conditions, environments, and sensor data. This will ensure that the system performs reliably in real-world scenarios, even when rare or extreme weather events like hailstorms or dust storms. Expanding the data set scope ensures that the autonomous vehicle is prepared for a wide range of driving conditions, making it more robust and reliable, and paving the way for safer autonomous system in the future. Thank you.